Hi. In the last video, I spent some time working on the ALU adder and cleaning up the clock for the emulator. Today, I do want to focus in a little bit more on the clock and spend some time wrapping that up. My goal today is to create that as a module within the emulator and something that I can turn around and immediately turn into schematics in KiCad. If everything works the way I want it to, by the end of this video, I should have a KiCad schematic that I can then turn around and place onto Breadboard. Let's see what we can do about that. Hi, I'm Adam. I'm still building a 16-bit computer from scratch. I'm no expert here. I make lots of mistakes. So many mistakes, I've actually had to reboot my computer build. I hope you will find my journey interesting, and I hope you will join me as I learn along the way. At the end of the last video, I mentioned that the clock has a bit of a problem that needs to be solved, and I want to demonstrate that. So if I slow this way down, just to help illustrate it, what I can do is I can switch back and forth between run mode and single step mode, and I may or may not get a clock out of that. And certainly the clock I get out of it may be a very short cycle clock. So I need to fix that so that the clock itself only recognizes that it's changed at the start of the clock cycle or the rising edge. And I can do that with a latch. All right, Adam, hang on a second. You said that adding latches was bad. Adding registers was bad. Well, yeah, I did. Or at least I implied it. Here's the thing, though. I need to make sure that things happen on the rising edge. And in this case, the state of the clock is actually a 1-bit wide register that needs to be latched with the rising edge. That's really the only valid time that that state can change. And so that's what I'm going to do is I'm going to create a 74 LS or HC 74 HC74 IC. And that has two latches on it. I need to latch both the run condition, so this LED here, and I need to latch the single step condition, or this LED here. Now this is implemented as a SR latch, and so I will effectively turn this into a 1-bit register by putting a D-type latch activated on this square wave because it doesn't stop oscillating. Let me get the 74 HC74 IC developed, and then we'll come back around and tie that latch into the clock so that I only get state changes on rising edges. Well, here it is, my newly minted 74HC74 dual D-type latch. And I've got my pin configuration here, the actual pin states, constructor, destructor, my trigger for the first updates. Here's the important piece here. I've got my slots, which will process updates, and I've got my signals, which will signal updates out. So effectively my inputs and outputs. The inputs are less than trivial, and that's because of the specific behavior related to the clear and preset pins. So here's the function table that describes that. On preset, when that's low, it doesn't matter what happens with the clock. It doesn't matter what's going on with the data pin. The output goes high, the inverted output goes low. Similarly, on clear, the output goes low, the inverted output goes high. But when both preset and clear are low, I have a special condition where both Q and inverted Q are high, and it is an unstable condition such that I have to trap that and figure out exactly which state the pins are going to fall back on. Now this also sets up a bit of a race condition, which would be the same in hardware. Which one would potentially happen first, releasing preset or releasing clear, if I was to wire it up that way? It's not like I'm going to go after this behavior. But if I was to do it accidentally for some reason, would I have preset go high before clear went high? Would I have clear go high before preset went high? And would the same thing happen in hardware as would happen in my emulator? And the answer is it probably would not happen in the same order. And that's a function of how this emulator is written. This emulator is written as a depth first processing basically of a tree, where all the different signals process deep all the way down one pin first, all the way to its end, and then kind of traverse its way back up, executing any additional slots for any particular signal. Real hardware all happens in parallel, and it more resembles a breadth first, or going wide across each level, before it goes deep into any additional children. And at some point, I'm going to have to come up with some method to change this from depth first to breadth first on my emulator. Okay, so with that said, the implementation, and I'll show you just one of them here. On clear, I check if the state goes low, and then I have to manage the Q1 pin based on whether or not both of them are low or not. And then if for whatever reason it goes high, I check if they were both low. I haven't updated clear one or preset one yet. That happens down here. But then if they both were, then I just go ahead and update one of them and send out the appropriate signal. And then I finally update the state. Clear is very similar. A lot of copied code here. And then the clock, very simply on a rising edge, I just capture what it was. I probably should be checking to make sure that preset and clear are not both high, or are not, that both of them are high, neither of them are low. Because going back to the data sheet here, doesn't matter what the clock does, the preset and the clear override the clock. So I need to make that change. And here is that change. So I'm just checking to make sure that if either of them are low, then I'm done updating and I just simply return. Okay, and here it is. So let me start by slowing the clock back down again. So I've got a nice long duty cycle for the clock. If I switch it into single step mode, and if I do that right at the beginning of the clock cycle, what you'll see is that it does not take effect until the next clock cycle. In other words, the clock itself stays on so that you get the full duty cycle of that clock. Similarly, if I go back to run, that does not happen until the rising edge again. So it does not latch until the rising edge. So if I happen to go put it in run mode right after we switch up to the high edge here, it waits until the next rising edge in order to make that change. This is going to be a good change for the hardware, and I believe it's going to make things run better, especially if I switch from run mode into debug mode and try to single step my way through this. So what changed? Really not a lot. I added obviously the 74XX74 IC into the clock build. I don't use preset and clear, and I realized that I don't actually need the second latch on that IC. And the reason I don't is because there's only two states, and I had forgotten that the 7474 also publishes not just the latch state, but the inverted latch state as well. So you can see the 3 lines that I added in here. Well, 4 lines that I've changed. I added the clock so that it processes the clock associated with the latch 1. I took my set reset latch and output its Q result into the data pin, and then both the Q and inverted Q outputs of the latch get passed on to the AND gates, taking the place of what the set reset latch was providing. Looking ahead, there's a couple of things that I also want to add into this, and I want to walk through those real quick with you. Okay, so what are these 2 signals that I'm talking about? The first is the reset signal. Now the reset is coming from the power supervisor or a manual reset using a momentary push button. The power supervisor pulls the signal low, but it's also an open collector, meaning that it, rather than pulling the signal high, it basically disconnects itself from the signal. And some external device, typically a pull-up resistor, would pull the signal high. So what do I want to do with that? Well, on reset, I believe I want to put the CPU into run mode. Well, to do that, what I can do is I can AND that signal with the signal coming off this run button, which is an active low signal leading into the SR latch. The button itself is high by default, and the reset signal is pulled high through a pull-up resistor. Well, if I AND both of those together, as long as both of them are high, neither one is trying to reset. And I would stick that in between this button and the SR latch. This would be the set pin. The other signal to talk about is the break signal. That's going to come from the control logic, and it's going to be driven by an opcode so that I can actually programmatically drop the clock into single step mode for debugging. It's going to be just about the same as the reset signal, except it's going to operate the single step, which is the reset part of the set reset latch. But I've also got a problem because with that signal coming off the control logic being high for the entire clock cycle, I could end up in single step mode and not be able to get myself out of that by clicking on run until I single step past that instruction, allowing that signal to go high. So for that, what I want to do is I want to use a rising edge detector. So I found this document, and in it, it has several different combinational logic subcircuits, if you will, one of which is a rising edge or a leading edge detector. Now, similar to the button and similar to reset, what I want is I want on the rising edge, the signal here to go low so that I AND that with what's coming off the single step button before I feed it into the reset logic. And this is the circuit that should allow me to do this. Now they've got a Schmidt trigger NAND gate, and I'm not certain I need the Schmidt trigger, certainly not on what's coming off of the signal. So I should not have a problem with bouncing where I actually need to worry about the behavior of the Schmidt trigger. So what do I need to do? Well, I need a couple of AND gates added in. And surprisingly enough, I have two that aren't used. And what I want to do is I want to drop those into the circuit ahead of the set reset latch so that each one of those signals can operate that latch and change the behavior. Okay, I'll make those changes in code and I'll put in some temporary signals for that. Okay, so here's what the emulator looks like with those two AND gates added in. You can't see the AND gates directly, but if I hit break, it actually puts the clock into single step mode. That break signal would come from the control logic as if an instruction called BRK had been executed. The other one is reset, which puts the clock back into run mode, and that would come from power on reset or me manually hitting a reset button on the CPU. Now, I'm not going to walk through all the code changes because the next thing I want to do is collect everything related to the clock and put it all into a single module that would then be placed onto the emulator effectively as a single unit. And then that should then allow me to switch over to KiCad and make all of those connections relatively quickly. Let me get the clock module written. Let me get the clock module written and settled in the code, and then we'll come back and talk about how I can take the code and turn that directly into a KiCad schematic. And here it is. What I've done is I've created a clock module group that appears on the screen, which now has all of the components that were part of the clock included in it as different groups. So externally I can break, which will still put the clock into single step. I can reset, and that puts it back into run mode. Now those are externally generated signals that are taken as inputs into the clock module. When I'm in single step, I can click my step button and all of that works as it should. So with that now, what I did is I pulled all of the different components into a single class here for a clock module. And then I went through and performed a wire up procedure. Now this wire up connects each of the individual components. And for example, some things are set low, some things would be set high, and others are actually connected up. And then my two external signals that come into this are wired up here. My published signal is taken care of in that wire up. What I see being able to do is to take this and use that as a roadmap for creating the KiCad schematic. And that's actually what I want to get into today. And that's actually what I want to get into now. This is ultimately what I wanted to get to in this video, is being able to create that schematic and see just how useful this is. All right, let me get KiCad fired up and let's give it a shot, see how well we do. Okay, on the left over here, I've got the components that I need. On the right is an empty KiCad schematic. Now, once again, this is not a complete list of components because I've only got the digital portions of it modeled. I do not have the passives like resistors and capacitors and things like that modeled. So it's literally just things that will drive the digital spaces of this. So my oscillator, which would be a 555 timer in real life, is going to be missing some resistors and capacitors and the like. So let me get the components placed for each of these. I'm going to do that quickly as a fast forward. And then when I'm done, we'll talk about how we're going to get some of these things wired up. Okay, and I think that's everything. So the next thing I want to do is I want to get two subcomponents wired up. One of them is the oscillator. The other is the debounced switch, which is the single pole double throw plus 555 timer. This is similar to what I've got on the board already, so I will use that as a reference as I wire those up. But I want to get those taken care of so that they are wholly prepared subcomponents here on this build. Okay, that will give me my analog circuits. That is the actual timer, and then my single step debounced. Let's call it what it is. That also includes the clock speed potentiometer, which is unfortunately named in the code. Now it's just a matter of getting the rest of these hooked up and some current limiting resistors for the LEDs and some pull-ups elsewhere and some ties to low elsewhere so I can get the rest of this settled. To do that, I've got these connections here. I think what I'm going to do is I'm going to shrink the size of this and improve the size of this so that I can get a little bit more on the screen. That should give me enough visibility so that I can actually pull these together. All right, so for the wire up, I need my potentiometer, which is here, connected to the oscilloscope raw input, which is effectively this 555 right here. Now let's see here. This is my AND gate number 4. Its output needs to be connected to NAND gate number 1, the A side input. So I need to start collecting these. All right, so there's that. And then my NAND gate number 1. Now my NAND gate, so I'm looking here, my NAND gate number 4 output needs to be connected to my NAND gate B input here. So I need to go find NAND gate number 4. That's my B input. From here, it's just rinse and repeat as I go through each one of these connections and make sure that I get them properly identified on the KiCad schematic. I did have a couple of them that were wrong. I had to go back and double check and flip a few things around. But ultimately, this was an easier process for me, I think. Yeah, it took a little bit longer to get stuff done in code. But once I had it sorted in code, it was much easier to get it translated into a KiCad schematic. Okay, then this should be the clock module. I've got inputs here, reset and break. I've got my output here, the ultimate clock. I've got a couple of internal labels here. What I don't have are power, ground, decoupling, my headers. So I'm going to spend a minute, get that taken care of. I won't bore you with that because that's pretty mundane, but what I did want to show you and what the intent here was to go through these connections and translate them into here. All right, I'll wrap up this down here. This is all the unused stuff and then the power, ground, etc. that I need for each of the ICs. And I'll come back and I'll show you the final schematic. And the schematic. I did have to flip one gate because I had A's and B's backwards. It would have worked the way I had it wired, but it wasn't congruent with what the code was, so I elected to flip that. Other than that, I think this technique worked out pretty darn well when I followed it. Again, I decided to go off on my own sometimes without actually looking at what things were. I've got down here my pins. I have separated the clock from the break and reset signals with the ground, and that should hopefully give me a little bit of extra stability here in the signal not bleeding off into the break or reset, so the clock doesn't accidentally drive sympathetically the signals here. And then I've got 3 power connectors, the intent being to put them on 4 corners of the board so I've got some stability. There's relatively few connectors on this particular module, so there's not a whole lot here that is going to actually support this board. So I'm going to go ahead and put extra connectors, and if I'm putting an extra connector, it may as well be power, because I've got voltage distribution problems already. So I may as well go ahead and make the best of that. I'm pretty pleased with how this worked, honestly. The process of putting the schematic together was relatively simple in comparison to what I think I was facing with some of the others. And I could very easily turn around and turn this into a PCB design very quickly. And I may even do that soon. Now, at this point, you might be asking, you've already got a working clock module. Why would you go about redesigning this? Well, that would be a very good question. First of all, I did not have the break and reset lines properly integrated, and I was going to have to come back and revisit those at some point anyway. Secondly, I needed something relatively small to test the process out with, and I am pleased with the process. Well, let's just say that this also allows me to rely a little bit more on my strengths. Now, I'm not going to say I'm an amazing coder, but I am far more comfortable writing software than I am building hardware. I'm learning on the hardware as I go, and I'm learning Qt as I go as well. And some things will change as I learn more and more about the framework. But I'm very comfortable putting code down and working through that process. I'm very comfortable debugging things in code. Debugging things in hardware is a little bit harder for me. So allowing me to work through the majority of those problems where I am most comfortable, and potentially save the worst of it for where I'm least comfortable, is actually going to speed the process along for me, I believe, once I get a good framework put together on how I want to implement this in code. And I think I'm drawing that picture in my mind. This code and the schematic I just did is going to be available on GitHub when this video is released. You're welcome to go have a look, and if any of this stuff benefits you in any way, do what you want with it. Please have fun. Now, what's next? Well, I've got a couple of things that are piled up here that I need to kind of get through. The register that I have designed is a fatal component and needs to be revisited, and that needs to be revisited from the ground up. I've got a computer backplane that I have to model, and that's where all the buses and everything are going to go. I've got the ALU that I'm going to start building out, and that's going to be built out into submodules as well. So I will have some work to do to pull that together. I'm going to pick one of those 3, and that's going to be our focus the next video. Am I going to commit this into PCB? Yes, eventually. Am I going to do that very quickly? No, I want to get more of the software built out before I start ordering more hardware and getting back into that. Ideally, I should be able to emulate a good part of what I've got today before I start looking at hardware again. So I've got a little bit of work to do in the software. We'll see you soon.